Welcome to the first lecture of the semester. This course is all about how we solve problems in computing, and so it makes sense to start with the definition of what a problem is and how we write one down. We do this using a really neat but conceptually simple idea called a formal language, which was invented by Frege, who is pictured on the slide. So we begin by introducing these. A formal alphabet is just a set of symbols. They can be any symbols at all, and we will denote alphabets using sigmas. Let's consider a few examples. The first example is the set of letters A, B, and C. The second is the alphabet for binary numbers, or propositional truth values in the syntax of engineering. The third is just several shapes, like a square, triangle, and diamond. And this emphasizes that alphabets can contain any symbols at all. Finally, the third is an infinite alphabet of all the natural numbers. Alphabets describe the symbols we are allowed to use when constructing words. Given an alphabet, we can write down words by slapping some alphabet symbols together in a sequence. For example, we can define words over each of our previous example alphabets. As you can see, we are just sticking symbols together to form a string of symbols, which we call words. For example, for the alphabet sigma 0, we define word 1 to be BBCA and word 2 to be ABA. But for sigma 3, W2 is 42, 42, 42. Okay, so we're just slapping symbols together to build what we call words. Words have an algebraic structure. The simplest word over any alphabet is the empty word. This word has no symbols at all in it, and we denote it using an epsilon. We can also compose words together by slapping two words together. Sometimes this is called concatenation. Composition has the empty word as its identity, and it is associative. This means that composition is a monoid. Each word has a length, which is simply the number of elements in the word. Sometimes we'll ask how many times a particular symbol appears in a word, as we denote here using the bars with the subscript A in it, where A is some alphabet symbol. We can use composition to define a special set called the Kleene star of an alphabet. This is named after the logician and mathematician and one of the founders of computer science, Stephan Kleene. A more elegant definition of the Kleene star is this one. Here we first define a family of sets indexed by a natural number indicating the length of the words in the set. For example, sigma 0 has words with 0 length in it, and thus only contains the empty word. And sigma 1 contains the alphabet symbols, because those are the only words with length 1. Then we build larger sets by grabbing words from the previous set and sticking each alphabet symbol together. Then we build the larger sets by grabbing words from the previous set and sticking each alphabet symbol to them. Then we can define the Kleene star as just the union of all these sets. That is, it's the set of every word of every size. We will now use this device to define formal languages. So a language is a set of words over an alphabet. In fact, the Kleene star, sigma star, is an example of a trivial language. It's just every single word that you can possibly think of over an alphabet. Let's consider a few example languages. Here we have several examples. Language L1 has only 3 words in it, AA, AB, and BA. Language L2 is the set of every word over A, B, and C that has exactly 3 B's in it. For example, the word ABBBA is a word in L2. Now, L3 is the language of every odd binary number. And finally, L4 is the set of words over 0 and 1 with only alternating symbols of any length. We use languages to ask questions. The questions we ask are in the form of what is known as the membership problem. This problem is concerned with some arbitrary word over the alphabet is in a language or not. And this allows us to treat languages as problems. In more detail, the membership problem amounts to asking whether an arbitrary word satisfies the constraint that is used to define the language. Here, P is a predicate over words. If it's true, then the word W is in the language. Thus, the membership problem boils down to asking if P of W is true for some word W. We can use this to state any problem in mathematics. Each component we have introduced in this lecture plays a part in specifying problems. An alphabet is used to describe the syntax, the symbols, we will use to define the data in a problem. Think of this as like writing a program. The alphabet is the alphabet of the programming language. Hint, hint, language. Then the words are the data of the problem. Think of these as the programs we write, where data is some data type or class. Then the language is the domain of the problem. This specifies the property the problem is dealing with. Then the membership problem asks if there is some data, a word, that satisfies the property of the language, and hence answering the problem. Let's check out some examples. In this example, we ask whether two graphs are isomorphic. We have an alphabet that allows us to write down a valid graph with both vertices and edges. Here a vertex is a number. Then we have the language of a valid graph. Finally, the graph isomorphism problem is the language graph iso, which pairs together isomorphic graphs. Thus, given two arbitrary graphs, G1 and G2, if they are isomorphic, then they are members of graph iso. We can also ask more familiar computational problems. This problem asks if a word is mentioned in a file called paper.txt. This is the question you answer every time you search a document on your computer. This class is about designing algorithms to answer the membership problem. Each model of computing will be able to answer some subset of the membership problem, and then we will build up the models to be able to answer more and more membership problems. The first model, called regular languages, is the simplest and is the topic of the next lecture.